Last time we built a neuron as a weighted sum, one number out, but a model has to do more than add, it has to decide to curve to say yes softly. So how does a number become a shape? Picture a vending machine, press a button, the input, and out comes exactly one snack, the output. Same button, same snack every time. That reliability is the whole definition of a function. One input, one definite output. The set of buttons it accepts is the domain. The set of snacks it can dispense is the range. Now plot it. Put inputs along the bottom, outputs going up, and trace the rule. If the trace is a straight line, the function is linear. Double the input, double the output, predictable, and a little boring. Bend that line and you get nonlinear, where small input changes can cause big interesting swings. Two nonlinear functions run modern AI. The sigmoid 1 over 1 plus e to the minus x is a smooth S that squashes any number into the range 0 to 1, perfect for a probability. RealU is even simpler. Max of 0 and x, negative in 0 out, positive in pass it through. A straight line with one kink, and that kink is enough. Here is the tie-in. A whole model is a function f of x given weights. Press the input button, get a prediction. Logistic regression is a weighted sum fed into a sigmoid, turning a raw score into a probability. And deep networks stack RealUs. Each layer is a function, the network is their composition, f of g of h of x, and that nesting is exactly where the power to fit almost any shape comes from. Here is the whole thing in one file. We will plot three functions on the same axis, a line, a sigmoid, and a RealU. Evaluate each at the same handful of inputs, then compose two of them and confirm the composed value matches doing it by hand. First, we lay down a grid of x values from -6 to 6, so every curve is drawn on the same domain. Then we define the three functions as plain Python, a linear rule, the sigmoid formula, and ReLU as a max. We evaluate all three at one probe point, x equals 2, and print the outputs so the curves have numbers attached. Next we compose, feed the linear output into the sigmoid of 2x minus 1, and compute it two ways, nested calls versus by hand, to show they agree. Finally, we plot all three curves in amber shades with the probe point marked and save the figure whose marked values match the printed ones. A model is a function you can draw. Next episode we leave the single curve and step into space, angles, distance, and the geometry that lets a model compare two things.